Okay, I'll start my last lecture in this overview of supermatrix method and its application to describing localization. So let me very briefly remind you what was our what we have already considered. We introduced Wagner and orbital model, which is associated with every site of a given lattice, 1, 2, or many dimensional lattice, an internal space of dimension capital N, and in this basis we think about our random matrix Hamiltonian as made of blocks of size n by n. On the diagonal we had just our old friend standard GUE matrices, and off-diagonal matrices were also chosen Gaussian random with all independent entries, but with variance parametrically smaller by parameter 1 over n with respect to typical variance of diagonal entries. And we discussed that meaningful thing to investigate is the expectation value of product of two resolvents, matrix elements of the resolvents taken. Okay, I will leave it here. Taken between 2 points of this lattice from I to j, and for technical reasons I explained that it's to preserve some natural symmetry invariances. It's nice to use these projector operators projecting on a given side. So our main object of interest is spatial behavior and also behavior dependent on z, with in the limit of small imaginary part of this z. So this z here is nothing else as just E plus I epsilon, where epsilon will eventually go to 0 as always in appropriate scaling limit. And we'd like to express to calculate this object, to perform the disorder average of distribution of all these entries, just following our standard route. So let me just go through this route again and again. I mean, it just will be repetition of all these tests, but just to be consistent, let us recall how we do it. So we associate with every, you see, we have here two resolvents, basically, with spectral parameter z and its conjugate, and precisely in the same way. I was very pleased that our, in fact, notations here are practically the same as Andreas used. I also use this plus and minus to distinguish variables which arise when I represent. So you see, the strategy will be our standard strategy. We will represent matrix elements of this resolvent using Gaussian integrals over commuting and anti-commuting, over vectors containing commuting and anti-commuting entries, and those those variables which are used to represent the first green function as Gaussian integral, they will be labeled with plus sign, and the second one they will be labeled with minus sign. I could use 1 and 2, but we have already these integers numbering, for example, sides of the lattice and also components of the vector. So I decided that just an extra plus and minus will be helpful, and I was very pleased to see that Andreas used precisely the same. So now pluses will, I explained, plus will always be referring to something, to the green function associated with parameter z and minus with z bar. So with imaginary parts are opposite, so it reflects in plus and minus. Okay. With this, now we represent, after all these 2 weeks, I hope that next step is practically automatic for you. So we just represent, as I mentioned, these green functions. Okay, small explanation, but it's in fact also, I hope, not very much needed after Andreas' lectures, that in all my presentation, I found it convenient to deal with ratios of determinants. Therefore, these ratios of determinants, or just determinants themselves and their inverse, always just simple Gaussian integrals. If you'd like to have rather matrix elements of the corresponding matrix, which is an exponential, you should put two variables just in the integrand. I think also it appeared explicitly in David Bridges' lectures, that in this way you generate just inverse matrix elements of the resolvent rather than just determinant of the corresponding operator z minus h. So we just use this fact, and we see that we have pretty standard representation for our correlation function, for this correlation function. We have, with every side of our lattice, we associate a pair of vectors, one containing commuting complex entries and denoted as phi with index, say, L, refers to site number L in our lattice, and its counterpart psi, which is Grassmann vector, vector containing Grassmann variables. And now we do all the familiar tricks. We first average over Gaussian distribution of GUE-like matrices which come on the diagonal of our block structure. It's easy. We precisely follow in the same route because these blocks just reproduce our old familiar GUE structure. It's precisely the same procedure. Then we also average over Gaussian distributions of entries which were off diagonal. I recall you that we had this kind of identity, something of this sort. If I remember correctly, if I comes here, then it will be minus v squared divided by n squared trace of AB. So we just use this to average over off diagonal blocks, and then at every side of our lattice we introduce our familiar object supermatrices, which are made of phis and psis precisely in the same way, just literally in the same way. Yes, please.
Previously we needed to generate something in the denominator.
This was in fact explained by Andreas, but I just repeat it. You see, just Gaussian integral, exponential minus, say, okay, with, say, okay, if I just refer, I think phi alpha, phi beta. Okay, this is equal to determinant of A times alpha beta.
Beta alpha.
Beta alpha. Thank you. Thank you. Beta alpha. Or in other terms, in order to cancel the determinant, I should divide by the same integral without without this factor. So in order to represent this determinant, I need Grassmann variables. Or alternative way on this, you always can obtain such objects, matrix elements of the resolvent, by differentiating a ratio of determinants over some duly introduced parameter in the matrix. In the same way as, for example, we use parameter t to generate trace of the resolvent when calculating Wigner's semicircular law. This is precisely the same idea. Or you may look at it using this identity. It's precisely the same. I hope now it's clear. We introduce at every side of the lattice this pair of vectors. We build at every side of the lattice corresponding supermatrices with boson-boson block made of phi's, fermion-fermion blocks of psi's, and boson-fermion and fermion-boson blocks of mixture, obviously. And then we notice that integrand depends only on. After that, we just look at our examples dealing with GUE, but here it will be not much different. Everything will be dependent only on these invariant combinations. What is nice also that pre-exponential factor will depend only on invariant combinations, and this is because we use these projection operators. We not only took some particular indices inside these blocks of size n by n, but we summed over all pairs going from one block to the other. And in this way, we also have, in pre-exponential terms, invariant combinations. And this allows us, we know that if everything depends only on invariant combinations, we can use, at every site, we can use our standard superbosonization tricks that we discussed many times in various fashions. So it amounts, at a technical level, it amounts to replacing RKs with matrices MKs, whose structure was discussed in detail and can be found, I think, in lecture 4. And integration over supervector made of phi k and psi k at given lattice site k should be replaced with integration over matrix mk, but we should also supply the factor superdeterminant raised to power n, where n is a dimension of internal space associated with every site. And just we introduce the same notation as before. Our main matrix, which dictates symmetry, hyperbolic symmetry of our model, it's diagonal matrix with first two entries, 1 minus 1 in boson-boson block and 1 minus 1 in fermion-fermion block. Or rather, I will reshuffle it. I explained why it's convenient to have a slightly different order of entries in supermatrices, because it's for a situation when we have this hyperbolic symmetry. And hyperbolic symmetry, just to remind you, it's associated with this plus-minus decomposition, with the fact that half of green functions, or precisely one in our situation, comes with plus sign of its of imaginary part of energy parameter or spectral parameter in its representation, and half comes with minus. So in order to write down explicitly the corresponding Q matrices, we remember that a more convenient ordering is B plus, B minus, F minus. So in this way, S matrix becomes just 1 minus 1 in this representation. So after these manipulations done, we arrive to the following compact, in the sense that simply looking expression. So we integrate now our relevant degrees of freedom over which we integrate are matrices Mk associated individually with every side of our lattice. We integrate over them And we see that the measure of integration over these mk's locally for a given k is precisely, in fact, if it hadn't been for this term, it will be just product of over all sides independently of our familiar object that we considered many times, just GUE, similar expression that we had for GUE. But of course, because of non-trivial coupling between different sides of the lattice, and also due to chosen scaling of the variance of off-diagonal couplings, we have an extra term which couples all these matrices non-trivially. For example, if we are just in one-dimensional settings, they're just this term will couple all nearest neighbors, but also in high-dimensional settings in the same way. And important, now you can appreciate why we need that scaling was very expedient, because all these terms, they do not have a large parameter n in them. So if we perform now, which we of course are going to do, the limit n going to infinity, it means this dimension of internal space associated with every side to infinity, then saddle point analysis basically comes back to the problem we already considered before, and these coupling terms, they do not interfere with our saddle point analysis that we already know.
Can you say again, what is this V, or is it just
okay.
non-trivial?
It was variance. You see, we had blocks. We had block structure of our original Hamiltonian, right? Here we had matrices which were precisely GUE matrices, independent, and typical variance of an entry in such a matrix. Okay, it was chosen to be 1 over n. Now, similar object, the variance of off-diagonal block here had what? First of all, was scaled differently, but also has a just control parameter. If v is equal to 0, all sides are decoupled. If v increases, coupling naturally increases. And this is precisely what we'd like to study. What happens if we increase v?
Can you tell what's that sum over n and n?
Okay, yes, thank you for the question. I should say it before, I think it probably already used it somewhere before. It means nearest neighbors. So I sum over all nearest neighbors in my lattice. All sides which are just related by one step in my lattice, whatever is this lattice.
And these K1 and K2 are connected?
K's are indices in my lattice. So I take two-dimensional lattice and label every side with K, which goes from 1 to the number sides of the lattice. And just to write this summation in concise form, I just use this notation. The summation goes over all pairs of indices which are describe nearest neighbors on my lattice. In one-dimensional case, it's simple. I just sum k and k plus 1, or k plus minus 1. But in high-dimensional setting, nearest neighbors, I think it's self-evident what the meaning of this.
When you say in the limit of n going to infinity, there's actually, well, no coupling anymore. Or these.
Why so? Quite opposite. There is the full scale of. No, I say no. I say no. I say quite different, very different thing. I'd like to, then I reiterate it. If I misled you in this sense, then it's yeah. In fact, what I say that my saddle point, this v and all terms which couple these matrices at different sides do not interfere because of chosen scaling. Do not interfere with saddle point analysis on site. So from point of view of saddle point analysis, it just I should take my old results from GUE analysis, and that's it. We know what will be the result of doing n to infinity. We know that basically we will have then matrices which live on some saddle point manifold. We discussed its structure, it's parameterized by these matrices T, but now it will be individually saddle point manifold for every side of the lattice. If it hadn't been for this V, say set V to 0, you have just decoupled formally its lattice, but every side does not know anything about a different side. So these T's live independent lives. These T's which parameterize, matrices T's which parameterize, or Q's if you like, which parameterize saddle point manifold locally. But because of the coupling, they know, they interact, like again Andreas always invoked in his first lecture, this analogy. They like, say, spins or vectors which interaction tries to align them in some sense. And we'd like to study this type of system, of interacting system now. So you see, GUE was essentially a very simple system. Now we have many coupled GUEs, non-trivial way coupled, in scaling way. And we hope that this will describe, after Wegener, we hope that this will describe the physics of Anderson localization, the resulting model. Okay, as I mentioned, we perform large n limit. Then all irrelevant degrees of freedom, apart from these matrices Q, are just taken to their fixed saddle point values. And but still we have some life, as we remember, at every side, because we integrate at every side over these matrices T, or equivalently you can say over invariant measure on this manifold at every point. In this way we finally arrive at our practically final object of interest, to the lattice version of the famous supermatrix nonlinear sigma model. This is a kind of statistical mechanical in inverse commas, but in essence it is. It's very close in its meaning to statistical mechanics of some objects which are not unlike spins, but they just live not on a sphere but on a more complicated manifold, which is product of a sphere and hyperboloid. This is basically the essence of the story. But of course, the fact that essential degrees of freedom live on this hyperboloid and could go to infinity plays a very essential role in the nature of the transition, and makes it very different from, essentially different from other, from magnetic phase transitions and all that. In particular, a very important role we shall see will be played by this epsilon, how it goes to 0. And we again later on invoke some similarities with usual phase transitions. But this is our object. Just look at it. We have a lattice. With every side of the lattice, now we associate matrix Q parameterized in terms of these T's. We integrate at every side over these T's, or alternatively, or you can think over Q's. And we have there are two terms in our exponent, or as physicists say, in our action. We have one term which just couples Q's at neighboring site on our lattice. And coupling constant is gamma. Obviously it's proportional to V squared, and also it's after the saddle point procedure we acquire two factors pi times rho, where rho is local density of states, it's mean density of states given in our model by just semicircular law. So if you just sit at real part z equals 0, it will be just pi rho equal 1. So basically we combine them, and this is a coupling constant. And we also have this term. Remember yesterday I was asked how we scale imaginary part epsilon. We scale it precisely in the same way as we learned from GUE. We scale it with 1 over n, where n is size of our blob, of our internal dimension of our internal space associated with every side. And in this way we arrive to pi times mean density of states times relevant parameter eta, and we will see that we need to investigate eta going to 0 limit appropriately. This is a lattice version of the supermatrix nonlinear sigma model, our main object of interest. Let us discuss a continuous version because it's useful for comparison and for some physical insights which I'd like to use later on. Remember, Q's are locally, it's Tk S Tk minus 1. So if you consider Qk squared, it's Tk. It's basically it should be 1 or something like this, and yes, it's 1. And then taking supertrace of 1. Remember, supertrace is difference between traces of boson-boson, fermion-fermion block. So we will then have that supertrace of Q squared equal to 0. Why I just remind this? Because this shows that this interacting term, supertrace QK1, QK2, can be immediately rewritten as 1/2, or minus 1/2 supertrace of QK1 minus QK2, where these K1 and K2, their indices on two sides connect, which are nearest neighbors in our lattice. And now in this formulation, it's obvious that if I just shrink lattice spacing, I mean just appropriately, one can say the following. What means shrink? That I go further and further away from my lattice, and it looks like a continuous medium. So basically it shrinks appropriately. Then it's clear that what happens, that I locally should replace differences with gradients. And this is a standard notion of continuous limit. You can do it, yes, you can do it in this way. Then in doing this limit, my coupling constant gamma will be rescaled also with lattice spacing, obviously. And the relevant combination, I write it, you will see in the moment why I write it in this form. I write it in the form pi times density of states times constant d. In fact, it's my definition of d from this nonlinear sigma model. And now I have a continuous medium, continuous, not lattice any longer, but just sample in RD, say in two-dimensional space. And with every point of this sample, I associate its own Q matrix, parameterized in the same way. And we also shall see why it's convenient. I just, instead of this eta, I introduce 2 times eta as a parameter and call it epsilon tilde. So we arrive at the following version of, this is what is known as continuum version or continuous version of the supermatrix nonlinear sigma model. Now the note is that physicists believe that they can arrive to this directly from the true Hamiltonian, one particle Hamiltonian, Laplacian plus random potential with potential delta correlated space. This derivation is not as controllable as one that I showed to you before. There are some leaps, and really it's present status of it that it's not that controllable. But still physicists believe that it should be the correct result if we manage to find some correct steps in the regularization procedure. So I take it for granted that this describes effective degrees of freedom associated with this problem. It's still an open problem how to arrive to it consistently. We can arrive to it, as I showed, as a continuous precisely to this form, as continuous version of lattice nonlinear sigma model, and I think this is clear-cut way. But for interpretation, I always will appeal to this interpretation. In particular, I will have in mind, and in fact, when they derive it, this D it's not coincident that I call it D, because in their derivation is precisely classical diffusion constant associated with, as we discussed last time, with classical particle diffusing by being randomly scattered by impurities in the sample, with L being a mean free path, a typical distance which particle goes without scattering, and V being typical velocity, which we, of course, thinking of electrons at Fermi level, we call V Fermi. Please.
So again, this question I once posed in the very beginning of your lectures. So in these sigma models that come actually from random matrix theory,
Yes.
The degree or the size of the matrices grow, of course, with the degree of the correlation function.
Yes.
And I remember, I just know from this physicist sigma models from Altland's book, and I don't remember that actually
It grows.
that it grows.
Only because they consider particular type of correlations which could be represented in terms of this nonlinear sigma model. If they just were interested in more complicated correlations, and sometimes we are interested in that, they could not avoid in enlarging sigma model. At least I do not know any mean of doing this. I think Martin will agree with me.
Can you be more precise in what is exactly wrong with these physicists? I mean, they're not stupid, but they do
No,
something.
nothing wrong. I mean, nothing wrong with physicists. I mean, they derive it using fine intuition, some steps. But you see, 99% of what physicists do is very hard. It's just matter of fact, very hard to justify every step mathematically. You see, there is an important thing. Being a physicist myself, I should understand. I think it's important for us physicists to understand two things. That there are things which are obviously true. We all believe they're true. But to really verify them on a level of mathematical rigor, even if they are sort of obvious, it's very hard, consistent, and sometimes ingenious mathematical work. So if you do not insist on being rigorous, I can derive it using practically the same steps in maybe another lecture. But if you insist on verifying and justifying every step, I don't think that anybody can do it.
It's roughly, I mean, first of all, we can say the names. Of
Yes.
physicists.
In fact, yes, Yefetov first, but with these lecture notes comes what I promised, some basic references where you can find everything. So
Fyodorov and also Melnitsky, who is here, is
Yes.
also the author.
yeah.
Now, the difficulty is that you cannot justify here the saddle point, the restriction to the sigma model manifold is justified by the limit n going to infinity. Second is rigorous. We can fight about whether that's a good limit or not. I claim it is, because what physically matters is the rate of transition. And if you make the density of states large and the transition matrix is small, keeping the transition rate fixed, that is perfectly physical. So there's no question that this is correct in this model. But now, if you don't have n, there's no n orbital model, and you cannot send n to infinity. You want to work with random Schrödinger. How do you justify this approximation? Well, there's no justification. What's done is you look at the expression and you say, well, I know that at the end of the day, what will matter are the long wavelength modes. Somehow your intuition tells you that you're going to get diffusion, at least transiently. Perhaps ultimately you localize because the dimension is too low. And the 1D theorems kick in, or the 2D intuition kicks in that you should become localized. But in the immediate regime, it should diffuse. Right? So if so, you have some idea what are the important modes. And they are the long wavelength diffusion modes which matter. So you go in there and you say, well, let me pick out those parts and throw away the rest. Okay, so once you've picked out those, you start seeing an expansion parameter. You have this kf times L, or the Vf times.
We will discuss it later on.
And then you can do this expansion in 1 over kf times L. And you can start seeing what is the justification of restricting to the cell. But no mathematician has ever been able to, follow this.
Yeah, but what do you pretend to do? Weak localization?
Me? Or
No, okay.
you mean no? Here, I mean, at the level of lattice version, definitely everything is there. Transition, localized phase, delocalized phase. At the level of continuous version, it's okay in 2 plus epsilon. I will discuss it later on. We will indeed, one can show by perturbative arguments or a normalization group rather that it predicts transition as well. So yes, everything is there. Everything is there.
And has the signatures of transition
Where?
in your model?
Yes, of course. Not only signatures, but just transition itself.
Okay, maybe I've mentioned it many times, but there should be something more than just this technical term in introducing all these hardship of supermatrices.
Yes.
What's the magic thing that makes all things look so good? Can you like?
Could you please reformulate your question? I mean, it's okay. I can tell you, in every physical problem, there is adequate mathematical, or if you'd like, just technical way to arrive to relatively transparent physical result. You can arrive to it by sheer contemplation of physical, or that's how Wagner, in fact, I think first arrived to the notion of nonlinear sigma model, and then he suggested that there is a background how to derive it. But you see, you should find adequate tools to arrive to correct and minimal physical picture. It's non-trivial job. This is a job what physicists do usually. Okay.
So one way of thinking is this: if we believe in universality, that this was an important theme in Andreas Ludwig's lecture. If we believe in universality, in particular at the mobility edge, critical exponents are universal and correlation functions are universal, then we can say this. There's one model where we have a controlled derivation, and we get this sigma model, and there's no question about it, it's just correct. Period. Now there's some other model which we cannot handle, and we don't have a controlled derivation. Well, we believe it's in the same universality class.
At least if we ask universal questions.
It should also be described by the same sigma model. So if we believe in universality,
And we believe.
we
Firmly. Okay, may I continue?
Perhaps we just believe what we can't prove, and we prove what we can.
That's correct. Okay, but let me, I think it's instructive to show, in fact, you see, we have some well-defined action in continuous version, and we have well-defined object, our Kij. Let us show that in some sense diffusion is there, because I claim that it's derived from here, but where is diffusion? Let us see that it indeed produces in some limit, and then we investigate what is the meaning of this limit. Diffusive form of our, we remember what diffusion should look like. It should have this k in momentum representation should be of the form 1 divided by dq squared plus epsilon, when both q small and epsilon is small. Let us see how it comes. You see, the meaningful names, as I mentioned, meaningful name for this object is nonlinear sigma model. Sigma model is just historic origin, but nonlinear is very important. These objects Q, like spins on a sphere. Sphere is nonlinear thing. But you may ask and try even under certain circumstances to linearize this theory. And basically it amounts to, if we deal with matrix Q, parameterize in terms of t's, so what makes it nonlinear? These square roots make it nonlinear. So let us expand square roots, and then we arrive at something clearly which is quadratic in these t's, and we can perform simple Gaussian integral and let with some quadratic form which will arise as the result of this expansion, and see what will we have. Here I just outline this. So we just expand these square roots. Later on we will see what in some sense what justify this approximation. So as t then starts with 1, obviously, if we expand on the diagonal. So first term in Q will be s, then will be, as it clearly, this linear off diagonal term, and then there will be next order we need it, quadratic terms at diagonal. Taking this, Okay, I leave it here. Taking explicit parameterization for these T matrices. T matrices, these T's, small case T's, they are still matrices. They depend on every point. In every point you have a matrix. Every point of your sample you have a matrix. But T is still a matrix. It's not scalar. So let us further write it in components, in just four components. We remember T1, T and its partner T21. They are just made of two commuting entries, TB and TF, and two Grassmann entries, alphas and betas, and their barred or conjugated counterparts. So we need obviously supertrace of Q times S, and we need supertrace of gradient square. So supertrace of QS is just given by supertrace T1 to T21. If you just look back here, obviously this term, the linear term, does not contribute to supertrace, obviously, because it's off diagonal. Then you just write it. It's simple quadratic form in all the involved variables. In the same way, supertrace of gradient Q squared, if you do not like gradients of it's not big deal, gradient of Grassmannian, but you still could have in your mind that we arrived to this as a continuum limit of lattice. So it's just difference of two Grassmannians and connected by this, by now very tiny link, which we just disregard. It's like a point. So it's gradient. It's very simple thing. And you immediately see that we obtain then, just, you see, all terms in the exponential just decouple with just quadratic form, diagonal practically. So you almost diagonal. It's not diagonal. In X representation, it's not diagonal. We should go to Fourier representation. Then it will be really diagonal. It just decouples into all modes. This we shall see in the moment. So we have now, in this Gaussian approximation or Gaussian field approximation, simple Gaussian, you have these pre-exponential factors which arose from it disappeared, but my object K was expressed as integral exponential of something and also some sort of Q matrices in front of exponential, in pre-exponential terms. So we need to keep them, because we remember these terms appeared, I recall your question, they appeared because we needed pre-exponential factors here. So they just, it's another disguise of the same phenomenon. So you need them. You can calculate this Gaussian integral. Literally, in order to calculate it, you expand in Fourier basis, because in Fourier basis, gradient looks just trivial. It will be Q squared, right? Q squared times Fourier variable, standard trick. If you deal with gradients, you see that your quadratic form just acquires in Q representation this simple form. And evaluating this Gaussian integral, you immediately see that we are happy. We arrive precisely at the form which we wanted to have for classical diffusion. So we see that linearization on a linear sigma model reproduces back these features associated with diffusion. Yes, please.
Like, give us a physical image of what this series is. Is it the number of scattering or is it?
No.
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 There is no physical.
Of what?
Of this series.
Series. Okay. This is expansion in. Okay, I can tell you. Now we have. You see, we see that at the lowest level we have this diffusion modes describing diffusion. Then there will be interacting diffusion modes. They are known by the name. Okay, in some situation by the name of diffusons, like other excitation, massless excitations. So it's really very similar to theory of interacting diffusing particles.
So these are the Hikomi boxes, you mean?
Will be, but I won't touch them. Their interaction will be described by Hikomi boxes. Yes.
You can say something like I said about Andreas Ludwig's representation. I appealed to the random walk interpretation. I said that if there was a boson occupation number, and when that was 0, that meant that this link was not visited by the path in the random walk sum. And if the number was n, it meant that this was visited n times. And you can think about the Q as being a continuous analog of this. So when Q is on a generalized sphere, and when Q points to the North Pole, that means you're looking at a configuration where the x, so Q is a function of x. So look at Q of x. If Q of x points to the North Pole, that means x is not visited by a path in the sum that you're doing by doing this integral. If Q starts deviating from the North Pole, that means
You wander a little
now
bit.
the paths you're now looking at configurations where the paths are visiting x. So there's some
Yes.
interpretation like this.
Okay, I'll continue if I'd like. Okay, so now we need to you see, we made some linearization. Yeah.
As I understood, our manifold had a compact directions, right?
One compact. It's a product. In some sense, you can think it is a sphere and hyperboloid.
But no, probably it won't be a good idea to integrate over the whole tangent space if one direction is compact. No?
Why so?
What's the question?
I'm a bit worried about integrating over the whole tangent space when there's a compact direction. So that is looks to me like there's a circle and we
Linearize it. You do not feel, of course, the topology of this. That in this sense, on terms of linear modes, you do not probe difference between hyperboloid or sphere. They look alike. But okay, this is a valid question, but we should do more. We should expand further, compare, and see. It's only perturbation theory, and perturbative effects, they're important to understand, but non-perturbative treatment can give surprises. So,
Function that you integrate
may I just continue?
actually supported around 0.
But you see, spin waves, if you'd like. Again, you have spins which live on, in some sense, they live on a sphere. But spin waves are just slow excitation, which just slightly deviate from North Pole, long wave excitations. They are meaningful. You calculate the interaction and so on. Similarly here, we like to expand further. It means just replace square root, not 1 plus first term of expansion, but further and further. And still, we always will have, after all these expansions, we will have Gaussian integrals to perform, but with higher powers in front of these exponentials. So we will see then interaction of these diffusion modes, and substituting them to formula for this quantum diffusion coefficient in front, in terms of this momentum or Fourier transformed correlation function, we can calculate correction. First non-trivial correction.
Just part of a comment one can make an answer. Think of David Bridges' lecture. What did he prove in the last one? He proved the theorem by Fröhlich, Simon, and Spencer. What was the content of the theorem? There was a breaking of ergodicity. The arithmetic mean of the field, the variance thereof, was bounded below by some constant. Physically, it means spontaneous symmetry breaking. Some direction is selected out spontaneously if you have an external field, and there are fluctuations around it. This theorem is the mathematical basis for this perturbation theory to be correct. The correct starting point and giving controlled answers. Now that's the case where the theorem applies. That's in 3 dimensions and higher. In 2 dimensions,
We will discuss it if I have time.
in physics, we say the Goldstone modes interact and stimulus is restored. We believe that, although that cannot be proved. We just think that this is the case. And so there you are entirely justified in being concerned about, is this a good expansion? I mean, the expansion does not know that we are wrapping around, and you might be worried that the perturbation theory doesn't see that, and you're quite correct.
But still, it will give
And
some meaningful
if you
insight.
don't take care of this, you will not see the fixed point that Andreas Liebwig wants to see in the sigma model, right? That comes from instanton effects, we believe, and they come from wrapping around the sphere.
Yes.
Not just by wiggling a little bit around some point of expansion, but by really seeing the global topology.
Yeah, I see, as long as
Yeah,
the field
yeah.
stays close.
Now, I would say that perturbation expansion is a natural thing to start with and to get some insight, and then you should of course take into account more refined features, maybe and certainly associated with global topology of your manifold. But still, let us proceed with what perturbation theory gives to us. The lowest correction to diffusion constant at given energy, I defined it, if you remember, here, is given by simple integral of this sort. And if I take just epsilon to 0, I take epsilon to 0. If you, as you remember, this is the correct limit in order to discuss a diffusion constant. I have this integral. I just, you see, Q here is a vector in d-dimensional space. So I write it intrinsic volume as dq times q to d minus 1. I do not care, everything here is spherical symmetric, so I do not care about angular degrees of freedom. I have this type of integral over modulus of q. But here I set minimal and maximal boundaries of integration in my domain. And this comes from physics, in fact. You should understand, first thing, it's necessary because you see, I deal with integral of power-like functions, so either it diverges at upper end or it diverges at lower end. So I should know which limits to set there. And this is given by the following simple intuition, that first of all, our sample is of course huge, but it has some typical size L, and if my integral diverges at upper limit, I should, so q's are of order of inverse sizes. So if it diverges at lower limit, I should remember that actually I should not take q smaller than 1 over L. On the other hand, in situations when it diverges at upper limit, I should remember that diffusion is meaningless on a scale which is shorter than mean free path, because we remember this discussion of mean free path. It's typical distance which a classical particle goes without experiencing essential scattering. So natural integration limits here just 1 over L. Here q maximum is inverse mean free path, and minimum q is 1 over L. And of course, we assume, in order to have a really picture of diffusion, we assume that our sample size is huge in comparison with this microscopic scale mean free path. First, consider just what happens if dimension is larger than 2. Then integral is perfectly convergent and at lower limit, so in fact you do not need, you can set this L to infinity. And you will see then that this correction is given by this expression. And now let us better understand the meaning of this correction just by writing down simple expressions which will be correct by typical. I won't take care of any, of course, coefficients of order 1, but just to understand what are these typical for electron at Fermi level diffusing in random potential, what in terms of these physical parameters, what is typical mean density per unit volume, and what is diffusion constant. To estimate mean density of energy levels per unit volume, we remember that this notion of electrons being at Fermi level that Andreas used many times, and how to estimate the typical density of energy levels per unit volume. You should just count how many these levels exist in your volume and divide by your volume and characteristic energy. Characteristic energy is Fermi energy, and now how many states typically in this volume. There is a very simple rule called semi-classical quantization rule, which attributes every quantum state to phase space volume. It means volume in coordinate and momentum space, 2 pi times h bar, and in this way we just write that this is a typical number of levels in our volume. Just size times it's sphere in first approximation, sphere in momentum space, so it's just typical number of corresponding levels. Now we immediately see how this mean density is expressed in terms of mass of our particle, Fermi momentum, and dimension of space. Now we should remember an expression which I presented a few times, that, and of course Fermi momentum is just velocity times mass, standard relation. And we should also remember about quantum mechanics that if we, by Heisenberg uncertainty principle, if we have particular value of Fermi momentum is just can be related with wavelengths of the electron, with which is lambda, and this is another parameter of dimension length which comes into this game. And we see after substituting all these estimates, we see that we come to a very simple formula that our quantum correction is just given by the ratio of wavelengths of our quantum particle to the mean free path raised to power d minus 1, where d is dimension of space, and here in this calculation we use that d is larger than 2. So we conclude in this way that quantum corrections to classical diffusion constant due to interaction of these diffusing modes, they are small as long as mean free path is much larger than de Broglie wavelength. Yes.
Can you justify also from the sigma model that the nonlinearity contributions are to be interpreted as quantum corrections, and the other?
But this is by very meaning of nonlinear sigma model is this, because we derived it from particle in random potential, so we expect that there is a classical diffusion picture modified by interference effects, by quantum interference.
But why should it be the quantum part that comes from the nonlinearity?
You see, I showed you that first term just reproduces classical result.
Exactly, yeah.
Then corrections due to what?
Okay, so
What mechanism? Just interference. What else could modify classical result? There is nothing else beyond that, because only D comes, so it's classical.
You need to put H bar to 0, then you should get it.
Okay. We should, no. You see, if we are interested in, yes, if you count correctly H bars, you will see that everything is coordinated. But H bar is important to keep if you'd like to have correction. Okay. So we see that this is a condition of weak disorder, and in a sense that our first correction was small with respect to the main term. Okay. Now, what happens at strong disorder? We, in fact, may try to take one by one, analyze high and higher perturbation corrections. And in fact, we can set a powerful machinery of renormalization group. We've heard some version of it from David Bridges. I won't discuss it. We can develop this type of renormalization group. And the parameter which will formally justify it will be that we are close to d equal 2, close enough. And the outcome of this is that there is a prediction of a localization transition, so of vanishing that these quantum corrections kill D completely, kill classical diffusion completely, for any D larger than 2 at some value, at some non-universal value L of order of lambda, of this sort. I won't go to this. Let us discuss what happens if D is smaller or equal than 2. Then it's easy to see from this integral that at small q it will be divergent, and we now should employ the fact that that minimum q is just 1 over L. And one just noticed that corrections are logarithmic. Okay. And if we're serious about comparing first, it's natural, I mean, it's standard physical procedure. Of course, we have the whole series. We do not have just first two terms, but it's very meaningful procedure, I believe, to compare first correction to the main result and to see what when this will be of the same order of magnitude. And we see that basically, if this shows that just at lengths is exponentially large, large by exponent ratio of L to lambda, exponentially large in comparison with this microscopic scale mean free path, correction to our classical result becomes of the same order as its main term. And physicists interpret it, although it's just first correction, but there are more refined techniques. Again, one can employ renormalization group and all that. But this is an indication of the fact that for larger LC, diffusion is killed by quantum interference. At least this is standard interpretation, and also it comes in more refined picture. Now one can also...
That's for systems with time reversal.
Yes, but this was the only class which I considered explicitly in my derivation. Of course, there are some refinements of this statement, but I won't go to...
You have the Hermitian matrix?
Yes, I had from the very beginning.
But now you're talking about the real symmetric.
Ah, okay. Yes,
class.
yes.
You derived one class and you
Yes.
a statement for the other class.
Ah, okay. Okay, but in fact, I only discussed here just the structure. Yes, indeed, you're right. Now let us go. So this is basically interpreted that d equal 2 is a kind of low critical dimension for this situation, for this model. One also can consider d equal 1 nonlinear sigma model. It's effectively physically it describes not just a chain with disorder, but just a wire. Not very much different from what we heard yesterday in these strips. I won't go into any detail. One can consider it. In this situation, one even can solve it exactly. And one finds that for 1D, basically this correlation function behaves like we expected for localized phase. It's just 1 over epsilon, and it just decays exponentially with characteristic length psi, which is proportional to diffusion constant. Unfortunately, no non-perturbative results are available in any, I mean, just say exact solution of the nonlinear sigma model we can only dream of for any d larger than 1.
Here one tomorrow.
Okay, but in specific specific case, yes, yes, indeed.
Yeah, also, it is possible to expand around strong coupling. So
Oh, you mean about opposite limit? Yes, one can make this expansion. Yes, but it's not again not non-perturbative, which covers all the range of parameters. We're interested in studying all the range of parameters, and particularly the transition is our main.
yeah, but the existence of the transition can be taken for granted if at one end of the for one extreme value of the parameter you can show it's localized, and the other end of the other extreme of the spectrum is extended, and by continuity.
Yes, certainly. I mean, no one question that on level of this understanding.
I would not say that the existence is in question.
Okay, from a rigorous point of view.
We cannot compute
Yes.
the model at the transition.
Yes, of course.
And we cannot
Okay. Yes, I mean that not that anybody questions that there is a transition. Even I insisted yesterday that indeed this is just a correct model to study the transition, but just that we cannot, so far we are not able to do it at the level of nonlinear sigma model. We just indeed see that in two opposite limits behavior is completely different, and therefore there must be a transition. Okay. Now let me just maybe give a few remarks before ending this picture about the idea picture. I mean, usually I write here always, but of course it's not correct, but because there are phase transitions like Koster-Staulis when picture of spontaneous symmetry breaking is usually not that much discussed. But in a standard way, I think also in David Bridges' lecture, the notion of spontaneous symmetry breaking is very useful in describing transition, many phase transitions. In particular, of course, the simplest example we have in mind is this type of magnetic transitions when we have ordered phase and disordered phase, and we can, for example, probe it by applying, say, magnetic field and see some, and then taking limit, thermodynamic limit of our system go into infinity, and then observing two different types of behavior for, say, for relation functions, depending on whether we have small magnetic field or do not have it. And let me just try to say a few words about viewing Anderson localization transition in these terms. So basically, we now have our theory in the following form. I'm now back to latest version of nonlinear sigma model. It's more convenient to discuss from this perspective. So we have this supermatrix nonlinear sigma model. If you'd like to calculate something like correlation function, we put appropriate things in the pre-exponential, and we have this model of interacting matrices, and we also have this parameter eta in front of second term. Let us just investigate what are symmetries behind this expression. We remember that these matrices T, which parameterize every Q individually at every point, they live on this, they parameterize this saddle point manifold. So they have this hyperbolic symmetry and in one sector and usual compact symmetry in another sector. So they were these variables that we discussed many times living on a sphere and hyperboloid. So it's obvious if you just forget about this second term, then supertrace of product of two Q matrices, of course, is invariant if we just conjugate both of them simultaneously with the same matrix T. And therefore, if we just make this rotation in all points of our lattice simultaneously, this will be the global symmetry or global invariance of our of the first and main, in some sense, term in our exponential, in our action. Now, however, if we impose that also second term should be invariant with respect to such global rotation, we will see that it's impossible for general matrices from this group, because just from the structure QS, we see that then S diagonal matrix should commute with T, and this is possible only if T we have only simple matrices T of block diagonal form, obviously. And this is from subgroup, which is just direct product of two U11 groups. We, however, remember that eventually, when studying localization, I explained it many times, we are mainly interested in this parameter eta tending to 0. So one can say that although our theory has this global symmetry, it is explicitly broken, or weakly, but nevertheless weakly broken by second term in our action. Okay, let me leave it. So, Developing this idea further, let us consider the following object. Let us fix one side of our big lattice somewhere inside, call it I, and take our exponential minus s with this s, so take only this part, and integrate over all q's, but not over q which sits in a given site I. Obviously, the result will be a function of q leaving precisely an I, because all other variables are just integrated out. Now, we remember that when we just set this parameter eta equal to 0, we have only first term, and it's invariant with respect to global rotation, one and the same rotation in all sides of our lattice. And then it would be naively we could expect that the same invariance just carries over to function f as a function of q. So the function is just invariant with respect to this conjugation for any t in our group. But this trivially implies that our function is just a constant, because it just q itself is obtained from s by rotation by t. So if it's invariant with respect to all such rotations, just f of q is f of s is just constant. Even one can show that this constant just is equal to 1, in fact. In such situation, if it indeed happens, it's natural to speak about preserved global symmetry or unbroken global symmetry of our problem. In contrast, if, however, we are able to show that the above invariance holds only with respect to this subgroup of the whole group, then in the limit eta to 0. Here it's appropriate to discuss the order of limit. We consider this integral in a lattice of number of sites, this modulus lambda, cardinality of lambda. We consider this limit, which is so-called thermodynamic limit, and then we set eta to 0. And in principle, it could happen that our function, we could envisage a situation, that our function won't be just trivial function, constant function, but will depend on q non-trivially. In this situation, it's natural to call, to invoke the notion of spontaneous breakdown of global symmetry associated with this problem. And trying to look at more detail, let me remind you of explicit parameterization for q which we used in this Yefetov variable lambda b and lambda f. In fact, one can show that in this situation, because of the residual invariance with respect to this group, f of q cannot be just arbitrary function of all entries of q, but must be a function only on these lambdas, lambda b and lambda f. Okay. So there is a guiding example which in fact drives our intuition on mechanism behind this transition, and this comes from analysis of this very nonlinear sigma model put on a tree-like graph which is known as Bertha lattice. One can just consider the corresponding lattice being not a regular lattice in d dimensions, but just tree-like graph. And then why there is an advantage of doing this, because in some sense model becomes solvable. We can investigate it to large extent. Why? Because of this loopless structure, basically this object that we introduced in order to characterize patterns of symmetry, it satisfies a nonlinear recursion relation. So investigating fixed points of this nonlinear recursion, we can get understanding whether there are fixed points which which correspond to preserved or broken this type of continuous symmetry. Analysis, which not trivial analysis, but can be done, reveals that there is indeed, for some value of coupling gamma, gamma critical, gamma C, there is phase transition associated with spontaneous breakdown of this invariance in the sense I described.
Can you remind us what is gamma?
Gamma, it disappeared. You see, S was equal to gamma times, gamma is parameter which couples matrices living on neighboring links of our lattice. So it's basically
New in the ideal model. That was new or?
no. It was gamma. In continuous version, it was the role of this was played by diffusion constant, but in latest version, it was gamma times super trace of Q, say 1, QK1, QK2, and some went over all sides of the lattice, which were nearest neighbors. So basically, if gamma equals 0, we have decoupled sides. If gamma increases, we have them more and more coupled. So with increasing this coupling, it turns out that this induces, at least for this particular model, indeed, one can show that it induces this type of phase transition with this pattern of symmetry breaking that I just described to you. Namely, basically, when gamma is small, so these various sides are not that strongly coupled. We expect that this corresponds to localized phase in some sense. Of course, if gamma is just 0, we have decoupled sides, so this is trivial localization in this sense. So for gamma smaller than critical value, this function indeed, okay, we should consider limit of this lattice going to infinity. This is done by considering essentially a fixed point of the corresponding nonlinear recurrence relation, which is satisfied by this function f. And these fixed points satisfy the following properties: that for small enough gamma, it indeed tends to 1, to the constant which I said it must tend to constant equal to 1, in fact, when eta tends to 0, but it does it very non-uniformly. Namely, it's independent on this parameter lambda f. It independs when eta is small enough. So we consider limit eta going to 0, so this 1 over eta scale just goes further to the right. And f depends actually only on lambda beta, while the product of this eta times lambda beta. So it practically stays 1 as long as lambda beta is much smaller than 1 over eta. And this eta can be made, of course, as 1 over eta can be made as big as you wish. We consider limit eta to 0. So indeed, this function, the symmetry is effectively restored. Your function tends to 1 in this way, but in this peculiar fashion. What happens at other side of transition, at gamma larger than this critical value? Effectively, system develops spontaneously internal lengths. In my notes I put here lambda, but then it interferes with the notion lambda of the lattice. So please correct in those notes you have. I just put here lambda tilde to distinguish between the two. So it develops spontaneously this scale lambda close to the transition. When gamma is close to gamma c, really this scale is huge, and it plays for function f a role very similar to 1 over eta, but please remember, here I already considered limit eta equal to 0. So no eta here. Still, my function f shows a non-trivial profile. So, and this is only possible, according to our discussion, if there is spontaneous breakdown of global symmetry. And just final remarks that this clear picture, in fact, has a relatively simple and I believe transparent physical interpretation in terms of scattering. And this will be in the last 5 minutes. I just give this picture, and this will be the end of the story.
Just one question. So we already heard a talk about this beta lattice. So
Yes.
what is it actually good for? It looks quite strange, and is it just
Okay.
has it got something to do with this renormalization? So that you
I should probably remove it, otherwise there is.
It's also there.
so is it somehow related to the kind of lattice that this hierarchical lattice, for example?
Not really. But it has hierarchical structure in it, but in different sense. It allows to, you see, how to calculate partition function. It's very non-trivial job. There are some in 2Ds we can do it, but otherwise it's very difficult. But on this lattice you can, you see, I can tell you what I think about use of Bernoulli lattice in this situation. I think that it reveals the maybe in very caricature way, but it reveals pattern of symmetry breaking associated with this type of transition. It has some peculiarities which even this solution that I mentioned has some peculiarities. For example, it's not usual power law vanishing of diffusion constant at mobility h, which we expect. But there is good understanding how, at least I hope that there is good understanding, how to translate those results obtained on a Bernoulli lattice to real world and how to interpret them, qualitative understanding. Basically, difference is mainly in the fact that the volume grows with the distance between sides exponentially on a Bernoulli lattice. Because you see, it just branches. And in this sense, I would say that it corresponds to infinite dimensionality. It's not finite dimensionality. Because you cannot embed it in any finite dimension. It grows exponentially with not like power law. So I believe that really, since this is the only case when we can investigate the transition, it's important to look at this pattern of symmetry breaking which appears and how the mechanism behind it, and it will provide some insight. That's my point of view.
It's in some cases, well, the tree is a little bit like infinite dimensions, because if you took a random walk in infinite dimensions, the chances that it would walk away and find itself again, except by backtracking, are very small.
Okay.
So this we had the research seminar by Florina Hallasan, and so here this is, if you wish, the n-orbital generalization. She was considering trees where there was one state per node or per vertex, but you can put n states per vertex and send n to infinity. Keeping, again, the transition matrix element times the density rate constant, so that the Fermi-Golden rule transition rate is kept fixed. Then you rigorously derive a sigma model, and then in that sigma model you can actually control you can see you can make a detailed analysis of the phase transition. This is the only time we've ever seen in analytical work the precise details
Of this spontaneous symmetry breaking.
of this phase transition. So
I think it's instructive.
the drawing is not very good. So the drawing on the left should have a wide plateau. Because
Yes.
it's small.
You see, when
it's almost infinite.
okay,
Drawing that the left picture narrower than the right one, so it is completely misguided.
okay, it's difficult to write. It's very wide. But what I showed here that when this symmetry breaking, external symmetry breaking eta becomes smaller, it becomes more flat. This was the idea behind this drawing. And I think I also explained it quite clearly what we expect. So let me just finish with providing very simple and I believe physical interpretation of this spontaneous symmetry breaking mechanism, and also in some senses it allows quantitative predictions in some situations. So let us imagine that we have our lattice in 2D because it's easier to draw, but in any D, and you just have a wire, an infinite coming from infinity and attached to one particular node of this lattice, and you can use it to send and to collect waves to this sample. So you just send your wave with some fixed energy from infinity. Because of this coupling to the node, it enters the sample, it explores some vicinity of this eye, or maybe can go far away, and then it's in fact reflected and comes back to, we can collect it via our wire. So there are incoming and outgoing waves in this setup, and we can investigate how standard quantum mechanical construction. We just introduce scattering matrix, not unlike, in fact, scattering matrices that Andreas considered in his lectures, which just linearly relate amplitudes of incoming waves. Here, just one wave. Of course, I can imagine many such wires attached. Then it will be larger scattering matrix. But for my goals, just one will be enough. And in this situation, scattering matrix is in fact scattering number. It's just one number, S, which relates amplitude of incoming and outgoing wave. It depends on the energy, and I use this its argument energy, complex energy Z. And it's a relatively simple exercise. One can relate it to the interesting object, the objects we studied all the time, to diagonal element of the resolvent of Hamiltonian describing this lattice in the absence of our wire. You see that if Z, important thing here, this resolvent itself, we know that if we just set Z equal real, we are in trouble along the spectrum, because it will diverge at all points where H has its eigenvalues. But if you look at this object, it's well defined for every real value of Z. It's a simple exercise again to verify. One can use just alternative, different representation, and just it will be explicit in that form. I can show it. That it's well defined for all values of real Z. But in principle, I'd like to keep this small imaginary part of Z, which played so important role. But please remember, if my sample is finite, for any finite sample, and I keep Z real, just explicitly, my scattering matrix is unitary. It means, in this situation, unimodular. It's just pure phase. And this is a simple fact related to the conservation of flux. As much flux going out as comes in via this sample. However, if I introduce this small imaginary part of energy, then immediately unitarity is lost by obvious reasons, because then my matrix elements of the resolvent will be complex number rather than real number, and from the representation here you immediately see that it's just not unitary. And then it turns out, just to make long story short, because we already should finish, one can relay, in fact, it turns out, and also this is a partial answer to Martin's reflection yesterday, that these Yefedov's variables are not very, he considered them not very convenient. I find them convenient in this setting, because I even can see the meaning of one of them. It plays important role, because one can relate by very simple and I think quite appealing expression, just the whole distribution of scattering matrix with this small epsilon to the object we just considered, to our function f, which knows about breaking of symmetry. And in this language, it turns out that basically spontaneous breakdown of this symmetry is nothing else as the following fact. You attach this wire, you introduce small, just tiny absorption in your sample, and then you consider thermodynamic limit. And the limit sample to infinity and this small absorption to 0, they do not commute in one phase and they commute in the other. And the physical meaning is very simple. In conducting in phase with broken invariance, part of flux is irretrievably lost at infinity, because it can escape to infinity due to the fact that we are in conducting phase. And then unitarity of scattering matrix is not restored in the limit eta to 0. But in phase with localized states, we probe effectively only finite volume, and everything is restored to unitarity. I think this is quite a transparent picture. Thank you. And just last remark, with the last lecture, I also provided some list of very basic references, and you will find, I think, I recommend you to go to them and to improve your knowledge of this interesting field. Thank you.
What about the off-diagonal elements of the scattering matrix there?
Pardon?
The off-diagonal elements of the scattering matrix.
In this setting is not applicable because we have just our scattering matrix, as I mentioned. It's not matrix, it's just number, because size of the scattering matrix is number of these propagating channels, and we have only one wire, so it's basically a number, but it's very meaningful number.
It's a little peculiar. He has the infinite plane or infinite Euclidean space, and at one point the infinite space is contacted to an extra direction through this wire. But through this wire he can send in waves and he can observe reflected waves. When the infinite system localizes, everything that you send into this wire has to go back out through that wire, and the S matrix will be unitary. However, when the infinite system is conducting and you send something in, some of it will be reflected, but some of it just goes to infinity, never comes back. So the S matrix becomes subunitary. But you fudge it, I mean, a true S matrix in quantum mechanics should be unitary, and it will become unitary if you take more care about the escape to infinity. You know, so this is a mathematical idealization. In the real world, there's no such thing as escaping to infinity. Somebody is always out there watching who's trying to escape.
But then this is an order of limit precisely does this. You do your volume to infinity. It escapes there.
Mathematical limit.
It escapes there. It
Infinite
escapes
volume
to infinity.
first, and then the removing the absorption. That's a well-defined limit in that case. So this is an insight due to Fyodorov. He wrote a paper on this. In that case, the S matrix is subunitary.
So from this point of view, basically the localization transition can be seen as spontaneous breakdown of S matrix unitarity. Of course, the same words, but just in different fashion.
There's another question here.
Yeah. About this gamma C, is it just proven that there exists one gamma C, or is this analytical version for that related to the better lattice?
Yeah, okay. I can more or less it can be shown on, of course, on only on the Bertollet, because we have access. You see, this is a nice relation. In fact, it can go a long way. Using this relation, we can say something non-trivial about phase transition, some critical exponent there. Okay, but it goes much beyond my modest goals. But of course, literally show it, one should use explicit solution on a Berthollet which is available. In other situations, just conjecture. What can it else be? If, in fact, if we believe in this picture of f being non-trivially dependent on both arguments, on these two things, it's unavoiding. You should have this. So it's just basically visualization of the same structure about f being just constant or being non-trivial function. This is a useful and I believe physical way of visualizing this a little bit abstract behavior.
Maybe I still raise my question well, but if assume you have something for gamma C expression, and
Yes.
if you express also gamma instead of previously you said it's diffusion, but now we put gamma. But if you express it, you can also make something like this.
I can investigate how this quantity 1 minus s squared, how it depends on gamma, where gamma is larger than critical. It will be 0 everywhere in the appropriate limit if I put epsilon really to eta to 0 in one phase, in localized phase. But it will be non-trivial function of gamma in second phase.
If I do again these quantum expressions that you did and
Yes.
replace the diffusion with lambda, do I get the same expression that if lambda is equal to mean free path, that's the gamma?
You mean you'd like to relate gamma to physical quantities, you mean? You'd like to appeal to continuous model. Okay, well, one should be careful. It deserves separate investigation. Morally, yes, but literally, how to relate it should be worked out. But in principle, gamma plays the same role of we've seen it as diffusion constant in this classical diffusion constant. You change it. It's coupling. It's more complicated.
But you'll get a renormalized stiffness.
Yes, you will have some normalization. Yes.
Gamma C, for example, depends on the coordination number. You can have
that's
a
my
lattice
question.
with 3 legs coming out of the verge, or 4 or m. The bigger m is, the smaller gamma C becomes.
Well, basically, it depends on disorder. Basically, it's a reflection. In microscopic sense, you change in disorder, you change gamma, you drive your system towards more localization. Or if gamma is larger, you drive it to delocalization.
That I understand, but if the result outcome is that says that this disorder or the mean free path should be much smaller than wavelengths,
And so what?
never happened. So
No.
that's why it's important to know what's gamma C in reality. You know what I mean?
Gamma C is just okay. It's your disorder which you drive through the transition. Transition happens okay in 3D. It happens when lambda is of order of yes. But this is precisely your control parameter.
You did the effort to translate your other expressions in terms of diffusion constant and
Yes.
the Fermi wavelengths, but you don't do it here. And
Because this is just coupling constant gamma on a lattice, and you do not have okay. If you have given
something like some length scale that you're
okay, one can relate it in terms of continuous version of nonlinear sigma model to diffusion constant, to classical diffusion constant.
I think that's a useful relation.
Okay, but it's obvious.
Okay, I would assume that everybody. Oh, there's still one.
And you apply the sigma model in the tail of the spectrum. If you go into the Lipschitz.
Tail, no. It should not work there. I think that definitely it works only deep inside the support of the spectrum. You should. It's also indication of this that everywhere enters this mean density, which when it vanishes, you are in trouble. You will be in trouble even in this simple Wagner model. If you really tune very close to edge of your semicircle, you won't have nonlinear sigma model any longer if you parametrically tune to it. So vanishing, if really your density of states is very small, it's not sigma model picture any
We have
longer.
a sigma model when we can derive it, and we probably have it when there's a scaling limit if we believe universality. So in the tails of something, it should not be universal, right? So then we don't expect this.
But even to derive it.
In different sense, it's universal, but in different
But even it's not nonlinear sigma model instead. It's different object. It's more complicated construction.
many things in your, but it's a different.
But it's not nonlinear sigma model any longer. It's something more complicated.
No, not necessarily. As long distances you have some.
Yeah, so there's different types of universality. I meant the type of universality associated with the critical points. Right? Anyway, I believe.
Well, that's probably sign. You should not say so.
I would imagine people are hungry. Do not forget, the participants, please do not forget to fill in this questionnaire. Yes. Be back at 2 o'clock for class cancer spectrum. Lecture number 3.